Two and a Half Admins, episode 31. I'm Joe.
I'm Jim.
And I'm Alan.
And before we get started, you've got another article to plug. Alan.
Yes. So Tom Jones wrote us a great article about understanding network performance. And talks about some of the tools and the difficulties in benchmarking and monitoring the network performance on a machine.
All right, well, there'll be a link to that in the show notes. Let's cover some news then. And Seagate claims that 100 terabyte hard disks will be around in about 2030. And the road to that 100 terabytes is going to give us with, 30s and 50s. So this is further evidence that hard disks are not going away anytime soon.
Their plan is to be about 50 terabytes by 2026 and 100 terabytes by 2030. They have a bit more of a breakdown where they also talk about where that will require HAMR, which is heat-assisted magnetic recording, basically using a laser to heat up the specific spot on the platter where you write to it, because flipping the bits when they're that close together, if you heat it up, you can be more exact. And then when it cools off, it's less likely to flip by itself too. And mixing in their Mach 2 system, which is the dual actuator, being able to deliver more IOPS off a hard drive. Basically, hard drives have had about the same number of operations per second for most of our recent history in hard drives. Like for most of the terabyte age, every drive from 1 terabyte to 20 terabytes can do the same number of operations per second, right? Because you've got the hard drives, the platters are this big and the head moves around between them. And the amount you can read off the platter while it's spinning under that head is gotten bigger. But the number of discrete places you can move the head, read from this place, and then move to a different place and read there hasn't really got any better. By having 2 heads, you can double that. Although still, if you're comparing the IOPS per terabyte to a 1 terabyte drive, a 20 terabyte drive, even with 2 actuators, is still a good ways behind.
I highly recommend that you pick up the Tom's Hardware link from the show notes and click in, by the way. Even if you don't want to read the article, it is worth it just for the animated GIF at the top that basically looks like Freddy Krueger meets Tron.
Yeah, kind of showing how the dual actuator stuff works.
Or how it might work in an imagined Matrix screensaver universe.
Right. But the interesting thing, they have their timeline showing how they're going to be at the 20 plus terabytes going into the beginning of next year into 2022. But by 2023, they're already looking at 30 terabyte plus hard drives. And like we said, 50 terabyte plus by 2026.
Those are useful predictions. But when you start talking about, how many terabytes you're going to have on a hard drive 10 years from now, yeah, that's fantasy. I'm not saying that they're wrong in the prediction, but that's like, well, we drew a curve leading from 1970 to now. And it seems likely that's, we'll be somewhere around there.
We're pretty sure we're going to be at least 100 terabytes. We may be wrong, and it could be 1,000 terabytes, but yeah. And they also talk about some of the difficulties, having to change the platter type. Modern hard drives that use PMR, or perpendicular magnetic recording, which was the big advantage that got us past like 300 and something gigs, uses either an aluminum or a glass platter, and then with a nanogranular film on it made of, I don't know how you actually pronounce the proper name for it, but COCRPTSiO2. It's chromium and something else.
Come on, Alan, you got this.
I don't remember. What's PT? I don't remember. Is that platinum?
Yeah.
But obviously with HAMR, you have the problem of aluminum platter probably not going to like being shot with a laser constantly, heating up and cooling down all the time. So HAMR relies on a glass platter with a magnetic film featuring high magnetocrystalline anisotrophic small grains of an iron platinum alloy, L10 FePt. So yes, it's platinum.
I could listen to you work through this all day, Alan.
Yeah, I'm sorry.
I think one of the important takeaways here, Seagate's talking about using HAMR, but the important letters out of that are the AMR. One way or another, if you want to get much more density out of hard drives, you're going to need some kind of assisted magnetic recording, because the issue is that the denser the information gets packed onto the medium, it needs to be more stable. It needs to be harder to flip those individual bits, because you end up having more leakage from the place where you actually intend to flip a bit to the surrounding areas where you don't. But then that leaves you with, you still need to be able to actually flip those bits. And there's only so strong of a magnetic field that you can exert from the head without, again, increasing the area that you're affecting. So the way that they get around that is with something like, HAMR using lasers, There's also energy-assisted magnetic recording that doesn't necessarily work quite the same way. And there's MAMR, microwave-assisted magnetic recording. But in all these cases, the trick here is you're using a separate process that makes the medium in a very small area a lot less stable.
More receptive.
Yeah, more receptive to you being able to flip it, while leaving the bits around it, still very difficult to change.
Yeah, and they talk like currently they're doing about 2.6 terabits per square inch right now. And they're looking eventually to get to the granular level where they can hopefully eventually get the 4 to 6 terabits per square inch. But getting past that, then they have to figure out how to actually get those granules to be in a bit pattern so they can get above 8 terabits per square inch in order to actually get into those 100 terabyte drives. At this point, they're like, we have an idea of how we would do it. It doesn't actually work yet.
Alan, you sent us a link this week to an article about Toshiba's flux control microwave-assisted magnetic recording FC MAMR drives. What's all this about?
Yeah, so kind of to get to Jim's point of, the new bigger drives are all going to have some kind of energy-assisted magnetic recording, whether that's heat-assisted or microwave-assisted or whatever. And so Toshiba's new MG09 drives come with flux control magnetic-assisted. And what is a flux and how is it controlled? I thought was a good question. So a group of Toshiba researchers have released a paper titled Magnetization Dynamics of a Flux Control Device Fabricated in the Right Gap of a Hard Drive Right Head for High Density Recording.
Come on, Alan. What's so hard about magnetization dynamics of a flux control device fabricated in the right gap of a hard disk drive right head for high density recording? That's easy.
You almost ran out of breath trying to say the title. That's all I'm saying.
As somebody who has to come up with multiple headlines every single day of their life, yes, I'm taking the piss. That's a terrible one.
Yeah. But basically, it's trying to control that magnetic flux like Jim was talking about earlier so that you can pinpoint the specific bits you're trying to flip and not accidentally have the flux flip other bits.
I think the best thing about Toshiba's approach is that it comes with terms that sound like they're lifted straight from Back to the Future. When they say, with MAMR, a spin torque oscillator is placed in the gap to et cetera, I'm just like, I am ready to go 88 miles an hour and, rocket off into the future with this thing, right?
Yeah. And apparently it's somewhat similar to Western Digital now has what they call ePMR, which is a drive that's only partially MAMR. I don't know what that's going to end up meaning in the long run, but...
Actually, I can tell you what that means in the long run because they include the technical description of it, and it's actually the same thing as Seagate's EAMR that they're already using in some consumer drives. Seagate calls it energy-assisted magnetic recording, and Western Digital is calling it ePMR, but in either case, you're applying electric current to the main pole of the right head throughout the right operation, and it basically just boils down to you have a secondary magnetic field, and you're adjusting the shape of the magnetic field as it actually impacts on the platter. It ends up being a narrower effective flux when it hits the platter than it would be with a simple right head without the extra super whammadine, current applied to the main pole. You don't normally apply a current to the main pole of the right head. You normally just apply it to the head itself. And by inducing that current, they're able to adjust the shape to be more precise.
I think the take-home message here is that the hard drive manufacturers are at least making noises like they are still innovating here. Whether they are or not, I don't know. I think they probably are.
Most of these ones, like the ePMR and the EAMR, are kind of stopgaps because full MAMR isn't ready for prime time yet.
Yeah.
It was kind of, the way we talked about a couple episodes ago was like, if we're going to build an array with these new big drives with this fancy, not well tested new recording methods, it's like, do I want to build my RAID array out of half of one type and half the other type in case one of them is no good?
Well, we're close to the release window, Alan, so you just go ahead and merge that into the kernel and you're done. That's a little callback to our last episode, folks.
Yeah.
All right, well, somewhat related to this is an article that your colleague Dan Goodin wrote recently, Jim. Bit flips when PCs try to reach Windows.com. What could possibly go wrong? This is a fascinating article about this researcher who bought a bunch of domains that were one character off Windows.com and then monitored how many times machines tried to connect to them doing Windows updates. And it turns out it was an awful lot of them. And the researcher, the hypothesis at least, is that it's from bit flips where the machine is trying to connect to windows.com or whatever.windows.com, update.windows.com or whatever. And that bit flip is happening and making it try and go to Windows 7s.com or whatever. It's possible that it's people just typoing it, but it's also possible that this is actually coming from bit flips.
Specifically, like if you look at in the diagram there, they have the ASCII of it. The H isn't really that close to the I on the keyboard, but if you look at the binary for it, it's just changing 1 0 to a 1, and that's when it becomes the different name. Like I don't think people risk type Windows and get windmws.com, but if you just flip a bit in one of the ASCII characters, then it turns into a completely different character, different than what you would get if it was typos on a keyboard.
Yeah, it would have been nice if the researcher had managed to get domains that were both an easy mistype and a difficult mistype, but an easy bit flip, literally just 1 bit off. Because if you had both, then you'd be able to, see the correlation of like, how many of these do you have versus how many of that do you have. But ultimately, through some other methods, the researcher was able to distinguish a lot of the cases where it was a typo, versus where it was a bit flip just by the rest of the URL.
Yeah, like if it's a deep link, it's probably not a typo.
What it really comes down to here is this really kind of shouldn't be surprising if you understand the way Ethernet works to begin with, because yes, they're not just Ethernet and TCP/IP. You absolutely do have checksums at every stage of the network connection, from one hop to another. But those checksums are not that strong. They're good enough.
Like I think on TCP, it's what you have 16-bit checksum across the whole 64K packet.
Yeah.
You have very little room in the header for the checksum. And it's just like a CRC32 or something super cheap, because in the 70s, you couldn't calculate a strong checksum.
Yeah, it's just a CRC32. For the inevitable cryptographers getting ready to yell at us, we're not talking about strong checksums regardless. We're talking about weak checksums. It's just we're talking about extremely weak ones now. And the difference is a strong checksum, there are no hash collisions with a strong checksum. It's 1-to-1. A weak checksum, you can have hash collisions. Here we get in the difficulty of the terminology again between human and technical. But even with a much less weak checksum algorithm, like the Fletcher used in ZFS, there's still a possibility of a hash collision where you have two different blocks that both match the same checksum. But in the default ZFS algorithm, you've got I think, what is it, Alan? Is it 2 to the 77th? I think, is the probability of a hash collision.
Something like that, yeah.
Yeah, 2 to the 77th. It's extremely high. Whereas for these network links, you're talking about a much, much more likely chance you'll have a collision. You're still going to catch, say, 9,999 out of 10,000, of these bit flip errors. But when you're talking about monitoring millions of connections a day, it's no surprise whatsoever that some of those, are going to be hash collisions where your checksum algorithm didn't catch a bit flip and something corrupt came through.
Well, in particular, the type of checksum used in TCP is designed. It doesn't have the same properties as some stronger checksums where, flipping 1 bit will make a very, very different output. These checksums are much more of a checksum rather than a hashing algorithm, in that they're basically just add up all the bits, and if they add up to the same amount, then it is probably okay. So one of the interesting properties of the TCP checksum is that if you're doing, say, NAT, and you're going to change the IP address on the packet, you don't have to recalculate the checksum for the entire packet. If you calculate the checksum difference of the change you made, you can just add that into the checksum and come up with the checksum of the new packet. I don't know if I'm explaining this right, but as you're changing the IP address and the port as you're going through NAT, you can calculate just the difference and apply that to the checksum without actually having to recalculate the checksum on the data. By just looking at what changed in the header, you can update the checksum basically differentially. And it means a lot less compute power required to do things like NAT. And so that's a useful property of that type of checksum. But the downside is you can change part of the message and it doesn't change the checksum that much.
Yeah, so the other thing behind all this is, like I said, if you're familiar enough with the concept of working at large scale, the idea that bit flips are going to happen in network connections is not a surprise. But one of the things that the researcher wanted to point out is that NTP, the Network Time Protocol, is a very old and, like, in its implementation in Windows, completely inauthenticated, and you can't verify anything. There's nothing built into the protocol. So if your NTP client ends up bit flipping its DNS request, and instead of trying to connect to time.windows.com, tries to connect to time.whndos.com, whoever controls that domain and the host that it's there at, if they've got a malicious NTP server, it can tell you that, it's the 20th of January in 2038, and you may very well have a buffer overflow that crashes your entire computer because it turns out that doesn't fit in a 32-bit integer. Or your computer might just get, incredibly confused about why all of a sudden, it's several thousand years BC.
Okay, this episode is sponsored by Linode. Go to linode.com/2.5 to get started with $100 free credit and 60 days to use it. Linode offers cloud computing solutions in data centers all over the world. Whether it's scalable VMs with a choice of major distros or one-click apps and stacks, dedicated CPU and high RAM instances, block and object storage, or cloud firewalls and DDoS protection, Linode has everything you need for your personal projects right up to managed enterprise infrastructure. I recently moved my website over to Linode and it was really straightforward. And when I needed a Mumble server for our Late Night Linux community meetups, spinning up a new VM for that was an absolute breeze. Everything's been running flawlessly since I set it up, and I love the peace of mind I get from the automatic backups. So go to linode.com/2.5, get your $100 credit, and check out Linode's great cloud hosting services and first-class, always available support. That's linode.com/2.5. All right, let's do some free consulting then. If you want to send your questions in for Jim and Alan, show@2.5admins.com, and if you've got any other questions or comments. Thank you everyone who's supporting us on PayPal and Patreon. We really do appreciate it. If you want to find out more about that, go to 2.5admins.com/support, and there's links there. And remember, for $5 a month or more on Patreon, you can get an advert-free RSS feed, so check it out. So Richard writes to us, since the first episode, I've started adopting ZFS and remote backup to rsync.net. Jim keeps repeating RAID is not a backup, and Alan adds it's not a backup if you don't have at least 3 copies. There are several threats that will require a backup, like robbery, elementary damage like fire or water, device failure, user-induced data corruption, etc. It seems that backup frequency, geo-redundancy, access control, and automation integrity are key factors for having a good backup. I have a production system on which I work, and I want to back up my data. I use scripts and automation to back that data up, but if I do 2 separate backups in parallel, any script issues or data corruption in the production will affect both backups. This seems to be similar to having the backup in a RAID configuration. If I use a chain of backups, then corruption of backup 1 can also propagate to backup 2. How do you set up your 3 copies and the data exchange and automation between them to really get the good backup Alan talks about?
So the first thing is you want to back up from a ZFS snapshot, right? You want your whole backup to be all of those files at exactly the same time. If you're just doing an rsync across a live system, files are changing while you're copying them, which can result in corrupt files, but also just the files you backed up at the beginning of the backup are X hours older than the files at the end of the backup. So taking the backup from a snapshot so that all the files are from the same time and they're all in a consistent state can be definitely the first part of that. And then to avoid the corruption thing, if you're chaining your backups, going from production to backup 1 and then backup 1 to backup 2,
don't do it.
It's just a matter of checking the copy there. If it's ZFS, you can do a scrub and make sure the checksums are correct before you go on and do the next one. But chaining probably isn't the right answer.
No, chaining is not the right answer. Chaining is not the right answer because it means you've got 2 points of failure in your backup C. We'll call your three systems A, B, and C, where A is your primary system, B is backup 1, and C is backup 2. Now, if you have A backing up to B, which then backs up to C, you have two different systems that if they stop backing up properly, then C doesn't get its new backups. That problem can occur on either A or B. I guess technically you could say all three, because C now also could be screwed up and result in that. But this is a problem that, in my experience, tends to show up surprisingly quickly because you have doubled your likelihood of failure by the time you get to machine C. The proper way to do this is generally to have both B and C do pull backups from machine A, and you simply have different retention patterns for C than you do B, or you can have, different frequencies. Sometimes it can be valuable, particularly if you're extra paranoid, to say, well, I want B to back up once every hour on the hour, but even if bandwidth permits, I only want C backing up once a day. And the reason for that, and we are getting to fairly extreme paranoia here, if you have a catastrophic replication system bug that might corrupt your entire file system, now to the best of my knowledge, this has never happened yet in ZFS, but over in the proprietary side of the world, in the early 2000s, the Waffle file system for, I think it was NetApp Sans, they had a really nasty low-level file system corruption bug, and if you replicated from a corrupt Waffle file system to another one, you would trash the entire thing immediately, including all snapshots. So in order to avoid that, you might very well want to have less frequent replication, to your coldest set of backups. Now, they're all technically hot in that, they're on 24/7 and you monitor them. But if you stagger that replication frequency, it gives you a little bit of extra time to figure out, oh no, this bad thing happened here. Let me make sure that doesn't happen over there. Now, the reason that you want pull backups and not push backups, and in this case, that means B SSHs into A to pull a backup from it rather than A SSHing into B to push a backup to it. The reason for that is because your production system is by definition the most likely to get compromised. It's what the attackers are aiming at. It's what has the most attack surface on it. And if and when your production system gets compromised, the last thing that you want to happen is for your attackers to immediately say, oh, I see where your backups are. You make these backups, every hour to B and every day to C. Let me go ahead and real quick and shell into those and wipe all that out. So that's why you want the pull backups.
Yeah, I think the thing I would add is, Jim kind of touched on it with mentioning retention policy, is make sure your backups aren't just a copy of your data, right? You want backups. So that means that on backup B, you have a backup from today and one from yesterday and one from the day before. Like you need multiple copies so that if you catch that user-induced data corruption, somebody accidentally mucks up the big important business Excel file on Monday and you don't notice until Wednesday. If you back up every night, then the copy from Tuesday night is screwed. And if you don't have a copy from Sunday night, then you can't restore it. And so you want those multiple points in time available. And so your backup shouldn't be one copy. It should be a series.
And we can't tell you how many of those to keep, but the term we're talking about here is archive depth. And we can't tell you what that ought to be. You need to think about it for your own situation and figure out what that is. Because I both have clients that are like, well, we need to be able to get the data exactly as it was a point in time 4 years, 3 months, and 2 days ago. And I also have clients that are like, anything older than a week, it might as well have just been deleted. That's completely useless to me. And, both of those cases are valid for those individuals' particular data and needs. So you got to figure that one out for yourself, but spend some time, figure it out, and craft your solution around it.
Yeah, and kind of to Jim's other point with the Waffle example and so on, maybe one of those three backups should be different than the other ones. Like whether that's using rsync instead of ZFS or just backing up to some file system that's not ZFS or something. So that if something does go wrong with either the script or the process or the protocol or whatever, all your eggs aren't in one basket. Kind of like we were talking about in the last episode with the OVH data center burning down. One of your backups should be at a different provider. Like if you're using Amazon, you can put it in 2 different Amazon data centers. But if Amazon cancels your account because you're Parler or something, you don't want to be locked out of your data. Also, if you're Parler, you shouldn't be taking my technical advice because I don't appreciate that.
Yeah, I was just like, I'm just going to sit here and let that Parler reference breathe. I don't like it. I don't want to be near it.
Yeah. But I didn't have a good example for why Amazon would kick you off their platform, but it can happen. But, it can also just be that the email address they send your credit card expired emails to isn't current, and suddenly you can't use your account because your credit card expired or whatever.
It could also literally just be that Amazon lost data. Everybody likes to pretend that, big cloud providers are perfect. They are absolutely not. Microsoft has lost my data. Microsoft.
Amazon's lost people's data too.
Amazon has lost people's data. Google has lost people's data. Data loss is a thing. Just because it's on a big provider with a shiny name does not mean that you don't need to be responsible for backing it up elsewhere.
Okay, Thor writes to us, "Hi, I'm setting up a home server and I would like to point my domain to my home IP for easy access to self-hosted services like Nextcloud. But I have a dynamic external IP address that seems to change every time my server reboots. How should I go about updating the DNS every time my server changes IP? My domain provider does not support dynamic DNS and recommended using another provider for dynamic DNS and pointing my domain to that provider, but I'm not sure if that would make the SSL hard to get working."
It shouldn't affect the SSL at all. Although, if you're using a provider for your DNS hosting, you want one that has a good API in order to integrate with the Acme client or whatever. So hopefully you would find one that has good dynamic DNS and a good API to add the text records for the Let's Encrypt validation. And that API could be used to do dynamic DNS even if they didn't provide a separate dynamic DNS integration. A DNS provider with a good API. I like Gandhi, but that's because I get a very deep discount for being a FreeBSD developer.
So there's a couple of things here. One, you can absolutely roll your own dynamic DNS if you're running your own bind server. You can do updates to your own bind zone yourself. It is a little bit of a pain in the butt to keep working right, honestly. The simplest answer is probably going to be to use a free provider like NoIP and just take, their garbagey, like, mycomputer.noiphomeservers.co or whatever. If you don't want to use that as the domain name that your services come from, that's fine, but you can just use a CNAME record instead of an A record.
The only place that won't work is at the root of the domain.
Yeah, that won't work for the root of the domain, but if you want to do nextcloud.thorsbox.com and you own thorsbox.com, then you can just set up nextcloud.thorsbox.com as a CNAME to, whatever weird, crappy residential thing that you get from your free dynamic DNS provider. Easy peasy, done.
That is definitely the easiest way to go. Because you brought up the Let's Encrypt thing, doing it with DNS is usually the easiest. So one way to do is whatever Let's Encrypt client you're using, find the list of providers they support with plugins. So I use acme.sh and they have support for Gandhi and like 40 other providers' API. And one of those is probably the best answer.
Although also, again, if you're doing the CNAME method that I was talking about, you don't need any special support because you can just do the text records as well as the CNAME on wherever you're doing your domain service right now.
Yes, we do something similar for Scale Engine when we use customer domains. We have them create the right CNAME so that their Let's Encrypt text records ends up coming from our zone so that we can control them.
Yep.
Right, well, we'd better get out of here then. Remember, show@2.5admins.com if you want to get in touch with us. I'm on Twitter @Joe Ressington.
He's on Twitter @AlanJude.
And he's on Twitter @JRSSNet.
Yes.
We'll see you next week.